All right, so for this first one here, we're going to expand irreversibly against zero external pressure. And one way to represent this is we have a container here, and there's a gas inside on one half of it, or one part of it here. This has an initial volume of 0.75 decimeters cubed, and then the whole thing is 2.25 decimeters cubed. And this gas is now allowed to expand freely into this empty area here. And there's no gas particles here, so there's no pressure that these are pushing against. They're literally just moving into this area here. And when that happens, these molecules, these particles, the gas doesn't have to perform any work. It doesn't need to do any work to expand. It's not pushing against the piston or pushing against some pressure. So the work is going to be zero. Now, the irreversible work is defined as the integral of P external times dV from V1 to V final. Well, if P external is zero, then the work is zero as well, just like what we just mentioned. Irreversible work is going to be zero joules here. Well, work is zero, and there's no energy being transferred as heat into or out of the system. There's no heat transfer, so Q is zero as well. Well, that means this change in internal energy, based on the first law, is going to be zero as well. And what's the significance of this? Well, if the change in internal energy is zero, that means the average kinetic energy of these particles is going to be the same. They're moving with the same speed. They have the same speed profile, the same root mean squared velocity. Because of that, the gas has the same temperature before and after the expansion. So the temperature is constant during this process. Good. And why is this important? Well, in order to find the change in a state variable for an irreversible process, we need to find some reversible path that gets us from the same initial to the final state. Because we don't have a really good equation here for this irreversible process. We just have this greater than sign. We want an equal sign. But knowing that the temperature is constant, we can look at this as a reversible process. In which an expansion is happening at constant temperature. So a reversible process, and we're having an expansion, an isothermal expansion at constant temperature. Well, we have an equation for this. We have an equation. A couple of videos ago, I derived that for you, so I'm just going to give it to you now. So the change in entropy for a reversible isothermal expansion is nR times ln of V2 over V1. And this is also going to be the change in entropy for this irreversible process, because with this process here, this takes us from the same initial state as this one, so they're both in the same initial state, to the same final state. The end result's the same. We're expanding isothermally, reversibly here, so that's like against zero external pressure in the limit of reversibility. We can use this equation here and literally plug it in. So we have 1.5 moles of our gas. Our gas constant is 8.3145 joules per mole Kelvin. And this is ln of 2.25 decimeters cubed over 0.75 decimeters cubed. Okay, and we can plug that in to our calculator. 1.5 times 8.3145 times ln of 2.25 divided by 0.75 equals negative 43. Did I do that right? 1.5. Okay, negative 43.73. So negative 43.73. And this is moles cancel out, so we're in joules per Kelvin here, 2 sig figs. So this is the change in entropy for this irreversible process here, negative 44 joules per Kelvin. Okay, so now for our next example here, I'll just bring it up here. So our other irreversible process is now against a pressure of 1 atm. And I'm going to represent this as a gas pushing on a piston just for convenience. And you've likely seen this before in your lectures or in textbooks, where we're expanding. It's now over a bigger area. We're going from some V1 to V2, and it's pushing against some external pressure. External equals 1 atm here. And it's an adiabatic expansion, so Q is 0. And we're doing work now. We're pushing against this external pressure. So the gas is performing work, but it's losing energy as work, but no energy is being transferred in as heat. So the temperature is changing. It's going from T1 to T2 here. And also the pressure of this gas will change as well, but we'll stick with volumes and temperatures here. Now, we're tempted to plug in 0 into the Clausius inequality here and say that the change in entropy is greater than 0 after we integrate it, which doesn't really help us, right? We want to get an actual number for the change in entropy, not a greater than or less than or something like that, just like what we did here. And similar to what we did, what we're going to do is we're going to find a reversible path to get to this final state based on this initial state. And the change in entropy using the reversible path is going to be the same as the change in entropy for this irreversible path, because we're in the same initial and final state from there. So how are we going to get from here to here? Well, one way to do it is we can, and I'll break this up, we'll expand the gas. So we'll expand isothermally. So we'll do an isothermal expansion. And pushing the piston up here. We're now going to a bigger area. We're performing work. But for it to be isothermal, we need heat transfer to occur. We need to inject some heat in here. Now you might be thinking, this is no longer adiabatic, so we can't do this, right? Because we're transferring energy as heat into the system. That's not allowed in an adiabatic process. So that's right, this is not adiabatic. But to get to the same state as this adiabatic process, all we need to do now is take the energy as heat out of it. So we've expanded it to the spot we want to be, but we've got this energy as heat that's gone in. Now we need to remove that energy as heat. And so we're going to take our Q and we're going to move it back out. So we put it in, but now we're to make it isothermal, but now we're going to remove it and we're going to keep the same volume. So this will be an isochoric cooling. So we're going to remove that energy as heat. And if we do that, we're left at the same final state as if this was adiabatic. So we're going to do this in 2 reversible steps to get from the same initial state to the same final state as this irreversible process here. Okay, well, look at this. This is an isothermal expansion. We just did this one, and I derived the equation in a previous video in this series. The change in entropy, we'll say for step 1, is going to equal nR times ln of V2 over V1. We also have an equation for the isochoric cooling, constant volume cooling. And again, I derived this in a previous video, and the last video we used it as well. So I'm just going to straight up write this equation. If you want to know the derivation, then you can kind of go back in previous videos. But it equals now NCVM ln of T2 over T1. This is the molar heat capacity times the number of moles to give us the absolute change in entropy here. So we're pretty good. We know the differences in volume, but the only thing we don't have yet is this second temperature. We don't know what temperature it is after the irreversible expansion. So how do we get that? Well, we do that by looking at how this 2-step process occurred. The gas is losing energy in the form of work, and it's gaining energy in the form of heat, as heat transfer. So in step 1, if we use the first law of thermodynamics, the change in internal energy equals the energy transferred as heat plus work. This is 0 because it's isothermal. So the energy transferred as heat is going to equal negative that of the work. And what about number 2? What's happening in the second process? Well, we're removing this energy that we added as heat. So we had heat transfer in, and the same heat transfer, same amount of energy as heat, is going to be transferred out. So if this is Q1, and this is just work, there's only one work, then these have to be equal and opposites. Q1 has to equal negative Q2. Right? Q1 has to equal negative Q2. Well, we can relate these two. So since Q1 equals negative work and Q1 equals negative Q2, we can say that the work done expanding the piston is equal to the same amount of energy that's lost when we're cooling it down. And by doing that, these two steps make it adiabatic. What's the work done? Well, the gas is pushing against an external pressure of 1 atm. So it's going to be the integral of 1 atm times dV. And how about the energy transferred as heat? Well, this is an isochoric cooling, right? So since volume is constant, work is going to be 0. There's no work being done. So if I write down here, the change in internal energy is equal to Q plus the work. There's no work being done in step 2. So the energy transferred as heat is going to be equal to the change in internal energy. And I don't know if any of you have performed bomb calorimetry yet in the lab, but we have an equation where we can relate these two, saying that the change in the heat capacity is equal to the change in internal energy with respect to temperature at constant volume. And now U is Q here, so we can say that the energy transferred as heat is going to equal CV dt here at constant volume. Well, this is dq actually. This is dq. So if we integrate this, we can write the integrated form. This is Q here. So if we integrate this from the initial to final path, this from T1 to T final, this here, we can put the integral here from T1 to T final, CV dt. Do you see that? Like this is Q and this is dq. So if you integrate dq, we get Q. And so this is Q here, and Q is equal to this, which is we just plugged into here. Okay, well, CV for an ideal gas is constant, and here is the constant, so this pressure comes out of the integral, negative 1 atm. Oh, I should put my limits of integration, V1 to V final, negative 1 atm, and this just becomes delta V equals the integral of this. CV is a constant for an ideal gas, and then we just have the integral of dt, which is literally just delta T. And from here, we can get the change in temperature. So negative 1 atm is, so V final minus V initial, 2.25 decimeters cubed was our V final, 0.75 decimeters cubed was our V initial, I believe. Now CV for an ideal gas is based on the equipartition theorem, N 5 over 2R. If you want, I can derive this equation. Just let me know in the comments, but I'm just going to kind of give it to you, or you could always look it up too. This is T final minus T initial. What was it, 298? 298 Kelvin. 298 Kelvin. Good. Oh, I guess we just need regular parentheses. Okay, so now we just plug this in. And now you may be tempted to solve for TF first and then plug it all in so that you're carrying less numbers and you're rounding less, that sort of thing. But on an exam, when you're maybe a little bit nervous and that sort of thing, I'd recommend just plugging in the numbers now so that there's less mental gymnastics in your head during an exam situation, even though you might be carrying less numbers, and that's kind of a faux pas, but I like to do this if it's an exam situation, kind of break it into a couple steps here. 2.25 minus 0.75, close brackets, so the left-hand side is negative 1.5. Could have done that in my head. Negative 1 atm. Negative 1.5, and it's atm decimeters cubed, and is 1.5 moles times 5 over 2. Now we want to use the right R, and here we have atm in decimeters cubed, so I'm going to use the 0.082061. It is decimeters cubed, or liters atm per mole Kelvin. A decimeter cubed is the same as a liter. And T final minus 298 Kelvin. Okay. Oh, I need to close my brackets here. So this right-hand side, we have 1.5 times bracket. I don't know how powerful this calculator is, so I better put some brackets in here. Most of them calculators you don't have to. Over 6. Okay, so 0.307725, 307725, is that right? 0.7725, okay. Moles cancel out. And I'm going to cancel these atm and decimeters cubed here. We're left with per Kelvin, so Kelvin to the -1, and T final minus 298 Kelvin. That equals 1.5, negative 1.5, unitless, of course. And so our final temperature is, we'll divide both sides by this number, transpose this to the other side. So be negative 1.5 divided by 0.307725 Kelvin to the -1, which becomes Kelvin when we flip it, plus 298 Kelvin. So this term represents the change in temperature from the initial temperature. And notice it's negative, so it's getting colder, which is a good sign because it's an adiabatic expansion. No energy is being transferred as heat into it, so we expect it to get colder. So negative 1.5 divided by 0.307725 plus, and I'm sure this calculator knows bed mass, or bed moss, depending on what you learned, is 293.1255. 293.1255. We're only significant to here. Well, this is 2 sig figs, so we'd really have 2 sig figs, but we'll do 3 here. 293 Kelvin. So this is our final temperature. This is our T2. So we can now 293 Kelvin. We can now plug it into here to get the total change in entropy. Just to keep this nice and easy to read, I'll write it down here. So the change in entropy of the system total is equal to the change in entropy of system 1 plus the change in entropy of system 2, which is, I'll rewrite it again, NR. The first step is an isothermal expansion of an ideal gas, so V2 over V1. And this one here is NCVM times ln of T2 over T1. So we'll just literally plug that in. Could factor out the N, but that's okay. So 1.5 moles times 8.3145 joules per mole Kelvin. Ln of V2 is 2.25 decimeters cubed over 0.75 decimeters cubed plus moles on this side, 1.5 moles. And CVM, this is for an ideal gas, it's 5 over 2 times R, 8.3145 joules per mole Kelvin. And ln of T2 is 293, 1255. I'll just keep the extra digits over 298. We won't really need them, but put them in there. Okay, so moles cancel out. We're left with joules per Kelvin on this side. On this term, decimeters cancel out. Moles cancel out here. We're left with joules per Kelvin, so that works out. Our kelvins cancel out, so all our units work out anyways. That's a good sign. So I'll plug this into the old calculator. 1.5 plus, times 8.3145 times ln of 2.25 divided by 0.75, close brackets, equals, I'm going to write this down in case I make a calculator error, and I won't be able to see the whole thing in one line. So 13.7016, 13.7016 joules per Kelvin plus 1.5 times, I better put brackets here. I don't trust this calculator. I'm sure it's fine. I should test it actually. 8.3145 times ln of 293 plus a bunch of stuff that doesn't really matter, divided by 298, close brackets, 8.3, 145. I think that looks good now. Okay, so negative 0.5142, negative 0.5142 joules per Kelvin. Okay, and then we'll add those all up. Take 13.7016 minus 0.5142 equals, and we only have 2 sig figs here, 13.2 joules per Kelvin. So 13 joules per Kelvin is our change in entropy of the system. Isn't that cool? We were able to do that, find the change in entropy for an irreversible process. All we had to do was find a reversible process in order to get there. Now, we still have some other variables to find out, to determine, but it's a lot easier. This change in entropy of the surroundings, what is that? Well, if we go back to our process here, no energy is being transferred from the surroundings into the system. So we'd expect there to be no change in entropy of the surroundings. Now, we might have thought the same thing for the system, but we found this reversible process and found out that there was a change in entropy. But if we look here, what's happening to the surroundings? Well, the surroundings are losing energy as heat, but they're also getting that energy back as heat. So there's no net transfer of energy as heat in these two steps. The surroundings are gaining energy as work, but work doesn't directly increase the entropy. So it's a wash here with this energy transferred as heat. The heat transfer comes in and it comes out. So the change in entropy of the surroundings are going to be 0 joules per Kelvin, and the change in entropy total of the universe is equal to the change in entropy of the system plus the change in entropy of the surroundings. So that's going to be 13 joules per Kelvin plus 0 joules per Kelvin equals 13 joules per Kelvin. It's positive. This is a spontaneous process here. Okay. And what about the change in internal energy and the heat and the work? Well, we know that there's no energy transferred as heat total. So that's 0 joules. The work in this case this is an irreversible process, so the work is the negative integral of P external dV. There's no other work. P external is 1 atm, so it's going to be negative 1 atm times delta V, which is 2.25 minus 0.75 decimeters cubed. Now it appears that our units don't work out very well, but actually they do. An atm is equivalent to 101,325 pascals, and a decimeter, there's 10 decimeters in 1 meter. And if we cube that, then we have our atm that cancel and our decimeters cubed that cancel. And we'll plug that into the calculator. Negative 1, which is, I don't even really have to include it, negative 1 times bracket 2.25 minus 0.75, close bracket, times 101,325 divided by 10 to the power of 3, which is just 1,000. So that's negative 16.988, negative 16.988. Negative 16.988, and the units are in Pascal meters cubed. Pascals meters cubed. We want it in joules, but that's what a joule is equal to. 1 joule is equal to 1 Pascal meters cubed. The work performed by the system is negative, how many sig figs? This would be 2, so we'll just say negative 17 joules. Great, all right. Well, I hope you really enjoyed that one. That was the irreversible adiabatic expansion. We needed to know the process of reversibility, whether it was against 0 pressure or against 1 pressure, and from that we found a a pathway using reversible processes in order to calculate the change in entropy and then all the other variables as well. Hope you enjoyed it. If you got some value from it, then feel free to like the video as it motivates me to make more. And thanks again. I'll see you in the next one. Cheers.